I am so pleased and more proud to introduce Dr. Kyle Grice, a chemist and recipient of the College of Science and Health 2024 Mid-Career Excellence in Research Award. I could say that it seems like only yesterday that Dr. Grice joined the faculty at DePaul. I will not. It seems like he's been here forever because of the lasting impact on the research profile that he has made and is making at this university. In the 10 and a half years at DePaul, Dr. Grice has published over 25 journal articles, most of which include undergraduate and master's students as co-authors. Through his research, an expansive network of internal and external collaborators, and the education of student researchers, Dr. Grice embodies the mission of the university. He is an agent of transformation. He is always thinking. He'll say, I read this cool article. Can we collaborate to do research in this area? Or I created a DePaul crowdfunding page to take my students to a national conference. He is always learning. He was trained as an inorganic chemist, but he has expanded into areas of biochemistry, organic chemistry, physical chemistry. Dr. Grice is a lifelong learner who excites everyone else to be one too. It is easy to find Dr. Grice's fingerprints in McGowan South. Today, he will share his research on addressing the carbon footprint left by carbon dioxide in the environment. Please help me welcome Dr. Grice.
Okay. So today I wanted to talk to you a little bit about what I've done over my time here at DePaul. Specifically, one area that I think attracts a lot of student attention and lets us think more about the world outside the lab while we're doing stuff in the lab. So, just really briefly, I'm doing lots of things as Panetta introduced, but most of it centers around metals and what they can do for society. So, for example, we'll talk about CO2 stuff today, but I'm also looking at metal complexes for breaking other types of bonds instead of CO2, and then have been collaborating with some metal-based drug folks, which has been really fun because I was never trained as a bioorganic or bioorganic anything, but learning how metals themselves can be drugs, or you can just model metal enzyme active sites. In fact, I have an NIH grant out on this area that I'm hoping to hear back on in March. And then this kind of segues with the CO2 reduction. Is one of the things I try to think about is how to do things in a more environmentally friendly fashion. Chemists, we often like stick things in big flasks with lots of solvent and boil it for a long period of time with lots of heat. And that takes energy and makes a lot of waste. So what can we do better, right? So that's what green chemistry is. That's something that we've built up some tools for. And so I've tried to think about that in terms of my work as well. But I'm going to talk about turning carbon dioxide back into something useful today. So to understand the carbon dioxide problem, right? So the environmental science folks or people who pay attention to climate change stuff, you probably have all seen this, but just very briefly, I want to make an argument here that CO2 is a problem, which shouldn't be too hard, right? So this is, I love plots, and I love finding cool plots in different places. So this is just types of energy that are being used in exajoules, which is just a big unit of energy. So you'll notice the stuff down here is coal, oil, and gas. That's the majority of what our energy is using, and it's overall increasing because our population is increasing, right? There's a pretty good correlation between the population and the energy use. We had a little dip here on 2020 for some reason, probably due to the pandemic, but I think the trend is going on. Okay, so we use lots of energy, right? And we mainly get it from natural gas, petroleum, coal, right? So that's what these are. This is one of these plots that shows like where things start from and where they go. The numbers here represent, some amount of stuff. Again, huge units. But what I just want to point out is that most of the thick lines and the big lines that go to transportation, industry, commerce, residential, all come from natural gas, coal, petroleum. So most of our energy is coming from natural gas, coal, and petroleum. These are all carbon sources, right? This is a nice plot from Lawrence Livermore National Lab. The national labs are great resources, not just for the tools they have, but the data they have and their figures. So, okay, so we use lots of energy. We use lots of energy from sources that are carbon-based, right? So there's been lots of discussion about, let's do all batteries, or let's do hydrogen gas, which is not carbon. And that's great and all until you start to look at what's called the net gravimetric and volumetric energy density. So just for a quick thing here, so energy density is like how much bang for a buck. Like if you have this much gasoline, how far can you drive your car, right? That's kind of like energy density, how much energy is in there. And you can think of it by volume, so that's volumetric, like how much energy, how far can you drive a car on a gallon of gasoline, right? That's volumetric. You can also think of it as mass, like weight, that's gravimetric. So like for a pound of gasoline, how far could you go? Now, that's interesting because it turns out there's lots of different things you could burn or use fuels, but things that have a high gravimetric energy density, you get a lot of energy from them by mass, which is good. Things that have a high volumetric energy density means you get a lot of energy from them for some set volume, which is good. So you want it to be high and high, okay? So you want stuff out here. Well, what's out there? Diesel, gasoline, jet fuel. That stuff is great in terms of energy density, how much energy you can get out of it as you use it. Batteries are getting there, but they're not quite there. So batteries are here. So if you have a battery of this size and you have gasoline this size, you have more energy from the gasoline. That's just the way it is right now. Now, batteries are getting better, but we're not quite there yet. And so this is also, I want to point out, this is a log scale plot, which always are misleading because this is not a linear growth. This is 10 times different. This is 10 times different. This is 10 times different. A log plot compacts everything down, and so it's actually not a linear thing. So these are further separated than they look in reality. So it's further away than that. And then over here, looks great. Hydrogen gas looks great, except that you get a lot out of the mass, but it's a gas. You have to compress it into a container, and so then you need a big volume to hold out that compressed gas, and that's why it's not very good on the volumetric side. And you can also imagine like crashing cars into each other that have pressurized gas tanks that then can explode with any flames. Is a bad idea. And so pressurized gases are a nice idea, but they just don't compete yet. So liquid fuels is the way to go. And that's also true is if you're trying to switch out everything we do, right, and we could go to all electric, but if we went to all gas pressure, we would have to change every single gas station. Because all of the gas stations we have right now are meant for delivering liquids, right? Your gas tank is meant for holding liquids, right? And if you change that to pressurized gas, everything would have to change. Every single gas station, every single car, right? So there's lots of challenges with this, even though people will promote it as saying, oh, hydrogen is great, it doesn't make any carbon, it's clean, blah, blah, blah. There's problems. All right, so liquid fuels are good, and that's one of the reasons we use them. I always love including this XKCD plot because, again, I just use a log scale plot. And so science tip log scales are for quitters who can't find enough paper to make their point properly. So this is the energy density of sugar, coal, fat, gasoline, and it's gravimetric by weight, and then uranium, so nuclear power, right? And so it turns out that nuclear power has an insane energy density and could drive and fuel everything that we would ever want to do. It's just that people are afraid of it, right? And so if I had an ideal world and I could say, let's change everything right now, I'd say nuclear, because that's the way to go. But people are afraid of things, and especially old technology, and disasters like Fukushima, Chernobyl, right? So there are reasons that people are fearful of nuclear. But energy density. So let's talk more about CO2. And I also like to always share some books I'm reading because I love reading science nonfiction, so history and society and science books. So there's this author called Sam Keen. He's wrote some great books. One called The Disappearing Spoon about chemistry, one called The Violinist's Thumb, which is about the history of genetics, and so the fly, how fly genetics was figured out. And then he wrote one called The Tale of the Dueling Neurosurgeons, which is neuroscience, the history of neuroscience, great books. His most recent one is called The Bastard Brigade, which is about the American spies that went into Europe to try to kidnap or assassinate German scientists who were trying to make nuclear weapons. And there's an interesting Chicago connection because one of the main spies who went over and nearly assassinated Heisenberg is a guy named Mo Berg, who was a White Sox catcher. And then he became an international spy. So, interesting connection. Anyway, so this book is about air. And so let's talk about air. And air is a mixture of stuff. It's mainly nitrogen, harmless. Then the oxygen that we breathe, and that gets used in our bodies, right? Then some other stuff like argon, water vapor, and some other small gases. And then CO2. So carbon dioxide, it's about 400 something. If you go, I looked at the measurement this morning, it's 422 ppm, and it's been increasing. And so these are all at partial pressures, but they add up to the atmospheric pressure. All right, so that's, and if you take Gen Chem, right, we can talk about the ideal gas law, we can talk about Henry's law, which is how Henry's law says if you have a gas over a liquid, that gas will dissolve in the liquid, right? And so, you know, that one of those gases is CO2. Well, where does CO2 come from? Well, so if you take a similar plot that I showed earlier, that's like all of our energy stuff, but now only the things that make CO2, right? So geothermal, wind, hydro, nuclear, solar, they don't really make CO2. You know, there's probably some CO2 made in making the stuff to use them, but they're not outputting CO2. But natural gas, coal, petroleum, and biomass probably make CO2 as well, right? Going to our carbon dioxide emissions, we're spitting out a lot of CO2. Most of it's coming from transportation and industrial use. And that transportation includes trucking to like, you know, trains, like moving stuff around. It's not just individual cars. But we're spitting out a lot of CO2. Okay, so why is CO2 a problem? Well, I mean, it's not toxic. You can breathe CO2 up to like a few percentage. It's supposedly, once you get up to a couple thousand ppm, it makes you a little lightheaded, a little slow, but not really harmful. Plants love it. It's what plants use to make sugars and grow, right? All their carbon input primarily comes from CO2, water, and then they use light to make sugars and such. That's photosynthesis, right? So that's, you know, not a problem. However, CO2 dissolves in water. It's a weak acid in water. So as we put more CO2 into the atmosphere, more CO2 goes into the ocean, making the ocean more acidic. This is ocean acidification. And you can explain that using the acid behavior of CO2 and Henry's law, which is more gas gets dissolved. And then it also contributes to the greenhouse effect, right, which is that idea that infrared light comes in, gets trapped. Other things do that too. Water does it. Water's a really good greenhouse gas. Methane is a really good greenhouse gas, even better than CO2. But there's just so much CO2 out there that it's a big part of the issue. And again, I'm not an environmental scientist, climate change expert. I'm sure there's like nuances and discussions in all of these. But the point is, to a full approximation, this is the issue. And I love this plot because it really shows that. So this is what's called the Keeling curve, which is somebody who's been measuring how much CO2 is in the atmosphere continuously. And there's this nice, you see this kind of like up and down, up and down, up and down. That's seasonal variations, right? So it's different depending on if it's summer or winter, but overall increasing in the atmosphere, all right? So this is the CO2 growing in the atmosphere from 1950s up to pretty close to today. So I said there's Henry's law, this idea that you put a gas over a liquid, it will dissolve. This is dissolved CO2 in the ocean. It's also increasing. There's lots of variability in the data, but roughly speaking, it's increasing. And so, sure enough, this plot here is the pH of the ocean around those sites. and it's going down, becoming more acidic. So that's ocean acidification on a single plot. Right? More CO2 in the atmosphere, that more CO2 goes into the ocean. CO2 becomes a weak acid in water, more acidic. Okay, so that's one pretty big problem with CO2. And then there's, of course, the overall greenhouse gas effect, right? So how do we treat this? Well, I'm the kind of person that thinks that when you try to tackle a huge problem, you got to tackle it as many ways as possible. I think that it's a, all hands on deck problem. I think everybody every scientific, technological, whatever can work on it. We're talking, chemists, biologists, environmental science, physics, right? Health. There's lots of ways to think about global climate change and how we can tackle it and its effects. So I think everybody should be involved. That's my personal opinion. So what can chemists do? We can make things, we can transform things. And so what could we do instead of just releasing CO2 into the atmosphere? And so one idea is let's turn CO2 into something useful. Okay? But what's useful? Well, some of the stuff that we already do in industry is making commodity chemicals, plastics, commodity pharmaceuticals, etc. And a lot of these come from kind of what's called consumer chemicals, like things we use a lot of. And so it turns out, for example, if for now, the way that we get carbon monoxide, which is a poisonous gas, but a very useful industrial chemical, like huge chemical plants are using it, working through a lot of it. They use it to make all sorts of things. So for example, they take carbon monoxide and they use it to make methanol, which is wood alcohol, is used in cleaners, chemicals. They can also use it to make diesel and jet fuel. But we just don't do that because it's cheaper to pull it out of the ground right now. But you can do it. You can literally take carbon monoxide and hydrogen and make diesel jet fuel gasoline. We know the technology. It's patented, it's studied, it's well done. South Africa did this when they had apartheid because there was embargoes about accessing petroleum. So countries have done this. Now, another thing you can do with methanol, if you could make it, is that you can use it to make, these are called plastic precursors, olefins, so that's ethylene and propane. This makes plastic. You could make plastic from these, which you could make from methanol. All of our acetic acid, if you go to a lab, a biolab, you get some acetic acid. That's not made from vinegar. It's made this way, from methanol and CO, industrially. Anything that's, like you look on the back of a shampoo bottle, it says something acetate. That acetate came from acetic acid, which came from this. And all of that right now is coming from natural gas or coal. But what if instead we use CO2 as the source? Because CO2 can be turned into carbon monoxide with catalysts. And that's what I study. And therefore, you could also turn it into methanol. So you could make all of these things from CO2 instead of what we're doing now, which is natural gas, petroleum, or coal. Okay? So that's the kind of grand vision. You can also make gasoline from methanol. This is making biodiesels. Whenever you make biodiesel, there's a little part of it that's not the bio part, and that's made from coal still. So the formaldehyde, which is used to make resins, like things like that. Anyway, point being, if we can make CO from CO2, then that's a good platform chemical that can make a variety of other things that we already know how to make. That's my kind of background argument of why what I do could have good effects against climate change. So to do that, we need to understand some things about CO2. So CO2, as I said, is a weak acid in water because it dissolves, makes carbonic acid, and then makes a proton, which is acid and bicarbonate, right? It's like sodium bicarbonates, baking powder, baking soda. And you can think of it, this is like organic chemistry kind of thinking. You can think of it as it's a neutral molecule, but it's got some polar parts. So something that's negatively charged can attack the carbon, something that's positively charged can be interacted with the oxygen. You can also think of molecular orbital theory, which is more advanced way of thinking. We talk about in chemistry and physics, right? And so you want to think about how can we actually attack this thing and break it down, right? Because part of the problem with CO2 is it's the most oxidized form of carbon. So when you burn something, that's what comes out. And then it's fairly stable. Despite doing this, it's a linear molecule. It's relatively unreactive at room temperature and pressure. So you have to do something to it to make it change. It takes some oomph. All right. I'm not going to walk through this whole slide, but I do lots of different things. I do things on small scales. So for example, this is one of the things I do is electrochemistry, which is adding or removing electrons, basically electricity, zapping something and seeing what happens. Because you could imagine using renewable energy to get electricity, and then using that electricity to drive a transformation that turns CO2 back into a useful chemical commodity. So you're recycling CO2 by using renewable energy. So you're not burning coal to then recycle coal. That would just make more CO2, right? So that's again why that tying something with nuclear power and back to renewable energy is important. But so like imagine the work I do is fairly small scale. So like imagine this is like a flask this big. Okay, I put a little bit of liquid in there with some stuff. And then I put in some metal electrodes, and I can study how things add or remove electrons from things. And so electrons, again, is just electricity, right? But it turns out to turn CO2 into something useful, you have to add electrons because it's the most oxidized form of thing. So you got to go to the reduced side, which is more electrons. And there's equations that govern this and things, and you get some interesting shapes out of it. This is like a plot that will come out of the approach I use. But the point is that the locations of like various signals in this type of plot allow me to figure out, okay, how many electrons are going in, how easy is it to reduce CO2 or hard compared to something else, and then also how fast is it? And that's an important thing, right? You want to make something that can turn CO2 over. It needs to be stable, efficient, fast, and cheap, right? And selective. That's like a lot of things there. You never get all of them. So like, the reason we haven't found a perfect system yet is because it's hard to get all of those things. So we might find a fast catalyst, but it's ridiculously expensive, or a efficient catalyst, but it's not rugged and it decomposes fast, right? So there's always problems, and that's just the way science is. But we learn something new each time, and we share what we learn, with our students, but also in publications. So. This has not been done. This is not to say that I'm the one who came up with this thing. This idea has been done a lot. Nature does this, right? So nature has enzymes that can turn CO2 into other useful things, which makes sense considering the fact that nature can do photosynthesis, right? But bacteria can do all sorts of other fun things, like they can turn dioxide into carbon monoxide, vice versa, or they can turn carbon dioxide into formate or vice versa. And the key thing is they use metals to do it, right? So I'm an inorganic chemist, so I love the fact that most enzymes have metals in them doing something important. People don't think about that much. Like I think 50%-ish of all enzymes have a metal in their active site or near their active site, and it's doing something important. So iron, zinc, cobalt, nickel, even heavier metals like tungsten. But so what chemists have done is they've built small versions of these with just a metal with some stuff stuck around it. And these are called complexes, where you have a metal with some things stuck on it. We call them ligands, L. Just various groups. And those various groups and the number and the shape really tune the reactivity of the metal complex. So in my postdoc, I learned a lot about this. The way we think of it is that, okay, we've got an electrode supplying electricity. We have some sort of catalyst, and the catalyst is something that does a reaction faster, right? And so you drop some electrons into the oxidized form of your catalyst, you make this red hot, reduced, very reactive thing, and that thing then reacts with your CO2. And it turns CO2 into something else, and then it recycles here, and then you drop more electrons in, right? And so you continue this cycle, pulling electrons from your electrode, electricity from a renewable source, and turning CO2 into something useful. And so this is the type of work I do in my lab. And when I started my postdoc and early in my lab here, we were mainly looking at a metal called rhenium. You might not have heard of rhenium because it's freaking expensive and uncommon. It's towards the bottom of the periodic table, but it works. And these lines, just trust me when I say the higher the better for the speed of electrons. This is a current or electron flow. And we found out that not only does this reduce CO2, but it actually also gets even better if you add water or methanol or some sort of proton source. So the reaction itself is turning CO2 and 2 electrons and 2 protons to make carbon monoxide, the product. And you can use different acids. And we looked at some manganese systems too. Manganese is much cheaper, which is great. But again, there's problems come along. So manganese turns out to be very touchy. It's actually light sensitive in solutions. So that's not something that you're going to like distribute in engineering systems. It's going to fall apart everywhere. So there's always issues. So another thing to think about, right, is scale up and how much you're going to make. And like, if you want to make a bunch of these or like have it go out and to be distributed, it should be cheap and it should be doable, right? So I love this plot too because this is also a log scale, but this is the abundance of different elements in the Earth's crust. So how abundant are they, right? And some things that are really far down there are actually not that rare. Like the rare earth elements, the stuff that's in our cell phones and things, they're actually not as rare as other things. But here's rhenium, way down there. That's why rhenium is not going to be the answer, I think, because it's so precious that it's going to be so expensive. So people have been spending time trying to look higher up here. So manganese, like I mentioned. I've been looking at tungsten, which is wolfram, and molybdenum, because they're much more abundant and much cheaper than rhenium. That's great. Okay, so here's some of the things I do in the lab. So we want to, again, we're doing chemistry, we're not doing engineering, so we're looking at small things. I want to see what's really going on. So I love using these called in situ experiments, where you're actually looking at what's going on as you're doing some chemistry. And so what I do is I apply some voltage from my potentiostat, that's like the electricity, and I can shine some light through the solution while it's happening and observe some things that are in there. It looks kind of like this. It's a little cell. It's about this big. And so I'll put my solution in there, put it in the IR spectrometer, plug it into electrodes, and turn it on and see what happens. And so this has allowed me to collaborate with a variety of people. And because I can observe a lot, I can observe anything that has a good vibration, which turns out it's not just Beach Boys, but good vibrations are things that show up strongly in the infrared. So this is not visible light. But things that have COs show up well. So we can look for different products. We can also look at speciation of metal complexes. So here's a known rhenium system. And these lines here are just different vibrations of these COs that I can observe as you do things. And the cool thing here is these guys here are things that react with air and water. You can't just make them on a bench, right? So, but you can observe them in situ with this technique from this air-stable precursor. So that's what a lot of chemistry I do. I make some air-stable precursors. I study their ability to get reduced and react with CO2 in situ in the cell. Do you have any math people here today? All right. Yeah. So the way you can tell the number of peaks you're going to see is from something in math called group theory and symmetry. And so we use group theory to understand how many signals you'll get from a various compound, which is kind of cool. All right. So this has allowed me to collaborate with people. This is a tool that I'm experienced with. So, for example, Alfredo Angeles Boza, who is at CNU Khan, and Mehmet Ertem at Brookhaven National Lab, they were working on this system. They wanted to study it some more, so they sent it to me, and we did the IRSCC, I call it, and observed what gets formed, right? And we did some other work, and we were able to publish this with my student Caesar in inorganic chemistry. And we kept going, and so a lot of what we do is we'll modify the stuff that we stick on the metal and see how that changes, or change the metal. So here we're modifying the stuff we're sticking on the metal, and we actually found out that not only can we make CO, we're actually making natural gas, and which is not easy to do and has not been shown at these types of systems before. So we're going all the way from CO2, which is the most oxidized form, all the way to natural gas, which is the most reduced form, which is pretty cool. And this is we published this in 2021, and so now we're trying to figure out how to make it better. But again, rhenium's a problem. I've also worked with manganese. Again, similar ideas. Again, these are collaborations where somebody else made the complexes. Me and my students did the IRSCC. Yeah, this was with a group from Texas A&M. This was from University of Wisconsin, Oshkosh. And so, that was not what I want to type. One more thing here, really quickly. So you'll notice that all of these systems have some kind of group that looks something like this on them, and they're called bipyridines or diamines. These seem to be required for rhenium systems. And so it's kind of like locked into only that works. And that's a problem. Like, what else could it work do? So what I'm trying to do is get away from this, just by being pulled back in by collaborators. Like, hey, you know. But so what we did, again with Caesar, is we just stripped that away. And we're looking at these commercially available, cheaper, much cheaper compounds. And they turn out to be much better catalysts without that. And so maybe we don't need that expensive ligand that you have to bind to the metal. Maybe we can use cheaper materials. And so we study this and we think about it in terms of like making some reduced species again in situ that you could then observe. And we can get some beautiful IRSEC. And again, these peaks, we're looking at our vibrations in the molecules growing in or going away as we're oxidizing or reducing them, making things in that little cell and observing how they work and observing how they react with CO2. So like here, this is just under argon, no CO2. This is with CO2. You can see some big differences. There's definitely stuff happening, right? And so from that, I can infer things like mechanism, how things are going, why things are going, and things like that. And you can do the same thing with the rhenium systems, but the rhenium systems without that what's called diamine system, diamine ligand you have to put on there, they don't work. They're not good. So it turns out we found that you can actually use molybdenum and tungsten, which are much cheaper than rhenium, and they don't need it without that. They don't need that thing that rhenium needs. So that's good. So now that we don't know that, this is kind of future work where we're going in my lab. Is we're now moving away to other types of things we could bind. They're cheaper, more abundant, and less expensive. And we're looking not just, we often will still make some rhenium compounds for comparison, but we're trying to look at cheaper metals that are also now working like tungsten, molybdenum, chromium, and looking at how we can improve the efficacy and speed of turning CO2 into something useful. And so this work's been ongoing for the whole time I've been here. I've got a couple students on the projects now, but I've had tons of students over the years doing all sorts of great stuff. And we all moved on to grad school, med school, et cetera. It's wonderful to see them move on and graduate. Like Jay recently got a PhD at Purdue. He's now works for Agilent, I think. Caesar, where is he? Caesar got his PhD from the University of Wisconsin-Madison. He's now working at a chemical company. Lucy is at Rosalind Franklin in med school, right? And so it's one of the really cool things is like students will help me in lab, and we learn some stuff, and then I can help them get on to the next place they want to go in their careers. And that's what really makes me happy when I'm here. Also, great collaborators. These types of problems are big problems. They can't be done in a vacuum. And so the more you think about collaboration, talk about other people, and think about other types of things you can do, the further you can get. So I've been really lucky to collaborate with wonderful people at various places to publish some of these CO2 reduction projects. The funding has mainly been internal, and then Louis Stokes Alliance for Minority Participation has been a very wonderful source of funding for some of our students, and which is Quinetta is the one who administers the grant. So if you have any students that would fit under minorities groups within that, they can get funding to do research. They can also go to some local conferences and talk to Quinetta about that if you're curious. And of course, the Department of Chemistry and Biochemistry and the College of Science and Health have been very supportive for all this work the entire time that I've been here.